Good morning, everyone. Right. So today we will talk about the Laplace transform proper, and I'm going to introduce it in a slightly alternate way. I'm going to introduce it through its properties because ultimately it's the Laplace transform properties that really matter. But I mean, it should be okay because you know the expression like there are many roads that lead to Rome. So regardless of how we approach the Laplace transform, you know, whatever path we use to approach it, it is the same thing. We are approaching the same thing, right? But before we go on defining the properties of the Laplace transform, and that's what I want to do essentially. I want to define the Laplace transform by its properties. I want to provide kind of like a justification. What is the justification? Why do we need to even do the Laplace transform? We said the Laplace transform is a kind of parameter, is a kind of parameterization, reparameterization. So I have functions that are based on parameter t. I just transform them to other functions that are based on parameter s. And the sole reason I want to do that is I want to simplify the solution of differential equations, or simplify, let's just say simplify finding the solution. Let's put it this way. So we want to simplify finding the solution of differential equations. That's the ultimate goal. All our definitions and properties of the Laplace transform are going to lead to this. If they don't lead to this, we would have failed. Okay. The basic properties we want to make sure that the Laplace transform has, of course, is that it has to be. We want to try to make it unique. We want it to be unique, right? Because if f of t goes to f of s, let's say this is a transform pair. So using this nomenclature, this is how I signify the transform. I say this is a function with respect to parameter t. It transforms into a function with respect to parameter s. Those two functions are equivalent, and the transformation is unique, meaning if I have some g of t, if it transforms to the same fs, then something is wrong, right? So this will become useless, because if I have fs, how do I know whether it came from ft or it came from gt? I do not, right? So I lost the invertibility. So that's why the Laplace transform, we would like it to be unique, meaning if I have, let's say I have the set of functions. Functions are points, right? So this is the functions in the t domain. I have the equivalent Laplace transform functions in the s domain. I want the transformation to be unique, meaning it has to be invertible. Each point goes to a point. I don't have two points going to a single point, so on and so forth. So those are the f of t's, let's say, and those are the f of s's. Okay. Another property we would like the Laplace transform to have is for it to be linear. Why? Because we're dealing with linear equations and linear systems and linear circuits. So it would behove the Laplace transform to also match that linearity. Meaning that if I have, hey, f of t, and I know that I can transform it to f of s, and I have g of t, and I know I can transform it to g of s, then I would want a f of t plus b g of t to transform to a f of s plus b g of s. Okay. All right. So we want those basic properties to hold. We want it to be unique so that it can be invertible. We want it to be linear. So we want to, for us to do this, let us propose. I want to propose potential transform. I want to propose it also for the discrete case, meaning our functions, the problem with our general functions that we're dealing with up to this point is that they are continuous, meaning they are defined everywhere. So they are defined at an infinite amount of points on the straight line, on the real line. Right? They are continuous. We wanna zero our attention at the beginning, only at the beginning. We will find out that the properties that we discovered for the discrete case hold for the continuous case. But we want to consider functions that are only defined at discrete points. So they are only defined at, let's say, t1, t2, t3, all the way to tn. Right? And how do we jump from the discrete case to the continuous case? Well, we just consider an infinite amount of points in the t-domain. Okay, so this allows us to write the transform from the t-domain to the s-domain, or from the s-domain to the t-domain as follows. I want it to be linear. For it to be linear, I mean, what's the best way of representing a linear relationship between a bunch of points and other points? It's linear algebra, right? It's by using matrix notation. That's why it's called linear algebra, because it's inherently linear. Right? So if I have f, so I said I'm considering only n points. So I have ft1, ft2, all the way to ftn, and then I have the s-domain representation. Again, I have, right? So this is the t-domain, and then this is fs. This is the s-domain, and the same thing, we have n s points. We don't have a continuous and infinite amount of s points, right? S parameters, all the way to Sn. Okay, so I have fs1, fs2, fsn. Right? In the discrete case, the transformation from the t-domain to the s-domain, or from the s-domain to the t-domain, is easier, because we have a finite amount of points. Because we have a finite amount of points, we can represent it by a matrix. Right? So I want to propose, we could put in anything in this matrix, right? Whatever we put in, it will still be linear. But remember, our goal, ultimate goal, is to simplify the solution of differential equations, right? I'm going to propose that to achieve that, we want to define our transform this way. So each of those elements in the matrix will look like this. So this is going to be e to the power s1 t1, e to the power s2 t1, all the way to e to the power sn t1. This is the first row. The second row is going to be, you should see a pattern now. Second row is going to be e s1 t2, e s2 t2, all the way to e sn t2. This continues downwards until we reach e s1 tn, e s2 tn, and this goes all the way to e sn tn. Right? I'm claiming that this kind of transformation is going to simplify solving differential equation. Right? And it's going to be linear because it's represented in matrix form. So let's represent it in summation form. So this tells us that, hey, f of t, and here I'm assuming t is t1 to tn. It doesn't matter, whatever properties we discover, they're going to hold even if I have an infinite amount of t's, even if I go to the continuous case. Right? But for now, it simplifies matter to just consider the discrete case. So this is going to be a sum over the function at each time is going to be the sum over s. Notice I'm changing s each row. So this is the sum over s of f of s. So I'm summing over s1, s2 up to sn, est. All right. So this is what the transformation would look like. Now I said I'm not concerned with the transformation itself, I'm concerned with its properties at this point. because I want to define the Laplace transform using its properties. Well, one major property we can deduce here is the translation property. So this is the relationship between the S version of the function, S domain version of the function, and the T domain version of the function. What about if we take the T domain version of the function and we translate it by lambda, shift it by lambda? So this is called the translation property or the shift property. Well, we can deduce this property easily by plugging T plus lambda here, right? So we end up with sum over S, f of S, es t plus lambda. This equals sum over S, f of S. I will use the property of the exponential function. This gives me e lambda s, est. Okay. Aha. So this is now the new function of S. Notice those two terms are only functions of S. This is the original est you have here, right? So this tells me I can deduce here that the transform of t plus lambda is this, right? So we can say that, hey, if f of t transforms to f of s, since the basic property implies, of the Laplace transform when it's written in this form, is that f of t plus lambda translated version of the function need to transform in this way. So it's the original fs times e lambda s. So I extracted a property from this equation. Now I want to go back and define the Laplace transform using this property. So instead of deducing the property, I want to propose this property as a definition. I'm allowed to do that, right? Hey, I could start with anything as a definition, as an axiom, right? But I justify it by doing this kind of like manipulation. And the beauty of this is that I derived it for the discrete case, but it's not dependent on the discrete case. Even if I make n approach infinity, meaning I have like a billion discrete times, right, I will still get the same property, right? It doesn't matter. Even if I go from the discrete case all the way to the continuous case by taking an infinite number of points on the real line, this basic property is still maintained, right? So I want to now kind of like forget about this and just focus on this property. This is what I want my Laplace transform to have as a property, and this is going to simplify the solution of differential equations, as I will show, right, in a bit. Now a question arises, what about translation? So we examine what happens if we translate the t parameter. But we're not done yet as far as defining the Laplace transform. What happens if we translate the s parameter? Right? So what happens if we have f of t? We said f of t relates to the Laplace s domain version using this equation, est. What happens instead of s, we go to s plus lambda. We shift s. Well, let's rewrite, right? So this is f of t equals sum over s, f s plus lambda, es plus lambda t, right? Again, use the exponential property, and it all comes out beautifully from the exponential and its properties. So this is going to be f s plus lambda, est, e lambda t. This is f of t. Notice something peculiar. Notice that e lambda t is not a function of s. I can take it out of the sum. I can take it out of the sum, and furthermore, I can take it to the other side. So this is going to be e lambda t. I can multiply both sides by e minus lambda t. E minus lambda t times e lambda t is just 1. Aha, notice this has the right-hand side form of the Laplace transform. Notice that the s function is this, and this is the Laplace transform of this function. right? So I've deduced that if f of t transforms to f of s, then e minus lambda t f of t translates to f of s plus lambda. Okay, so this is a curious result. We found out that translation in the t parameter is equivalent to this, multiplying by e lambda s. And we discovered that translation in the s parameter is equivalent to multiplying the time domain function by e minus lambda t. So there's like a minus there. Okay. And as we said, those two properties hold in general, even if we jump from the discrete case to the continuous case. So we don't have to worry about this matrix anymore and those equations. We just use them to get those two properties that we were going to show that we need to simplify the solution of differential equations. And those properties hold no matter how many points we consider. Even if we have infinite amount of points, those properties still hold. Now we are ready to kind of write down the defining properties of the Laplace transform. So those properties I'm going to write down next are going to be our definition of the Laplace transform. We'll find out later that you might have encountered like what's called the Laplace transform integral definition. We'll find out that those defining the Laplace transform through those properties will naturally also lead us to the integral definition. I think this is, by the way, superior to the integral definition in my opinion, and we'll discuss why later. But let's now pin down the definition. Okay. Definition of Laplace transform. And the definition is going to have 4 parts, right? So one, it's an invertible map. So this is a map from the t domain parametrization of a function to the S domain parametrization. Of x of t to the S domain parametrization of same. Let's call it x of s. Okay. So the picture is as follows. Let's say we have let's draw it in terms of sets. So we might have a bunch of functions, x of t, y of t. Each function is a point. So this is the t domain functions. So the Laplace transform is just a map. That's what's a map? A map is just an arrow, right? So if I have the S domain, the bucket of the S domain functions, so I have x of s represented by a point. So a map is just a relationship. It just takes this x of t, takes it to x of s. It's an invertible map, so that means it has to be unique. I cannot have y of t also go to x of s. That's not allowed. That doesn't make it invertible. Right, and this is, I can write it this way. Right, I mean, very basic property. It has to be an invertible map. Each of x of t each unique x of t needs to go to a unique x of s, and there shouldn't be any ambiguity about how do you invert. If you have an x of s, you need to know for sure where it came from. And the only way to ensure this two-way relationship is to have an invertible map. Right? A bit of a word of notation. The notation is written like this. So x of s, this is the S domain version of the function, is the Laplace transform of fx of t. You will see this notation, right? And we say that x of t is the inverse Laplace transform of x of s. L minus 1 means the inverse. So going this way is L, going this way is L inverse, right? And then there's an alternate notation, which we will also use a lot, which is as follows. X of t, yeah, the alternate notation is just representing both S-domain and T-domain versions of the signal or the function as a pair with an arrow in between. Okay. So this is property 1. Property 2 is that it's linear. Again, a basic property, and this simply states if I have two signals, sum of two signals with gains A and B, like this, two signals of this form summed together. So AX1 plus BX2T, right? Then from linearity, the Laplace transform needs to obey this linearity property. So L of this should be A L x1 t plus B L x2 t. Again, a very simple property. We can write it in the alternate notation as follows. So if x1 of t goes to x of s, x1 of s, and x2 of t goes to x2 of s, then the function a x1 of t plus b x2 of t is going to go to a x1 of s plus b x2 of s. So this is a property that we want to have because, I mean, we ultimately want to use this to help with solving differential equations, and differential equations are by themselves linear, right? So we should expect linearity to also hold here. Okay, so this is defining property number 2. Again, very simple. Now defining property number 3, and there are 4 in total, is that T domain and S domain translations are as follows, or not are as follows. Let's say have following property. If f of t goes to f of s, and I'm going to use the alternate notation for this, then the translation in the t parameter is going to transform as follows: e lambda s f of s, and then translation in the s parameter, fs plus lambda originates from this t domain parameter, t domain function, which is e minus lambda t f of t. That's it. That's the third property, and we justified this property by the manipulation that we did previous to this definition. Now I'm introducing it without any justification. That's something very common that is done when people work on those things, is that they kind of like do something for a specific reason, but once they arrive at what they need, they forget about that process, and they just introduce the result as a definition. So this is here, I'm introducing it as a definition, as part of the definition, as part 3 of the definition of Laplace transform. Part 4 is about seeding the Laplace transform, right? So we have those properties of the Laplace transform, and hopefully those properties are enough for us to figure out any Laplace transform. So invertibility, linearity, this basic property. But for us to start getting Laplace transforms for actual functions, we need to somehow seed it. We need to, by definition, assume a Laplace transform for one seed function. And hopefully, using those definitions, the Laplace transform for all other functions is going to follow. That's the hope. So property 4, or defining property 4, is very simple. It states that the Laplace transform of the Dirac delta function is 1, or I can write it in alternate form as follows: delta t goes to 1. This is a matter of definition. There is no reason that the Laplace transform of delta has to be 1, but as a matter of definition, we define it to be 1. Okay, so this is the fourth property, and we will find out now that using those 4 properties, we can find the Laplace transform for any function we desire. Okay, and that's it. Those are the 4 defining properties. I'm claiming we can use those 4 to understand the Laplace transform fully and to find the Laplace transform for any signal we desire or function we desire. Before going there, we want to discuss a bit the reason why this kind of transform is going to simplify differential equations. I haven't shown you that yet, so I'll discuss that next. Oh, okay, and remember also from the last lecture, we said we don't want to discuss functions really in general. We only want to discuss functions where we have a function multiplied by u of t, or a function multiplied by delta of t. Right? So we want to only constrain ourselves to functions of this form. What will happen, you see, in this topic is that sometimes we might omit the u of t. So I might write, I don't know, cosine of 2 pi t, right? But implicitly, when you do the Laplace transform, there is a u of t there. I might not write it all the time, but implicitly you can assume it's there. Right? We will only deal with functions that have either u of t or delta t tagged to it. If there is nothing tagged to the function, then the assumption is that there is an implicit u of t. Although we didn't write it down, it should be there. Okay. Now I want to show you, why does this way of defining the Laplace transform simplify differential equations? Well, I mean, it starts, what are the differential equations, what are they constituted of? They're built from differentiation and integration. So we want to show that the Laplace transform simplifies differentiation and integration. Let's start with differentiation. I have a function f of t, right? So what is and I'm taking f of t in general. This f of t might have u of t inside, it might not. But in general, what is df by dt? That's defined as limit h goes to 0, ft plus h minus f of t over h. Notice here we have ft plus h. We know how to deal with this function, right? So when we take the Laplace transform of both sides, right, let me take that Laplace transform of this. So this is going to be limit of h going to 0, and we know how to handle translation in time. Translation in time is equivalent to f of s, Laplace transform of f, ehs minus f of s over h. I can take f of s out, so this is going to be limit h goes to 0 of f of s ehs minus 1 over h. If h goes to 0, ehs approximately equals 1 plus hs, right? We can approximate the exponential function this way. So if I have an exponential function, approximating it close to 0, it can be approximated by a straight line. Another way of thinking about this, if you take the Taylor series expansion of eh to the power s, 1 plus hs squared over 2, so on and so forth, If h is small, you can ignore all the higher order terms and you get with this approximation. So continuing with this approximation, I get limit h goes to 0, f of s, 1 plus hs minus 1 over h. This cancels with this, h cancels with h, and we end up with this result. df of t over dt transforms to sf of s. This is a basic property that we get. This is a basic result. This is a result that we get just from applying the translation property to the definition of the integral. Okay, and this is why Laplace transform the Laplace transform is useful for solving differential equations, because it turned an operation, a linear operation that is kind of like, you have to do some calculus to figure out, to just multiplication. Multiplication is still a linear operation, right? S f1 plus f2 is just s f1 plus s f2. It's still linear, but now it's a simpler operation. It's just multiplication, right, by s. So multiplying a function by s to find the differentiation of it is much easier than doing the differentiation, right? So in this way, it can the Laplace transform simplifies differentiation. And well, what's a differential equation? The differential equation, d2 over dt squared plus d over dt plus something else, a, b, c equals 0, right? It's just differentiation, right? So here this is, let's say, y, right? So this is just differentiation twice, so this is equivalent. Each differentiation is equivalent to multiplying by s. So this is going to be a s squared ys plus b s ys plus c ys equals 0. So this turned, in the s domain, the differential equation turns into an algebraic equation. And algebraic equations are, again, much more easier to solve than differential equations. Okay, so yeah, we will show some examples on how to solve differential equations using the S domain, the Laplace transform. So we'll do that later. At this point, I just want to give you this result. Okay, what about integration? How do we transform integrals? So transformation of integrals, right? So I have the integral from some constant a to t f tau d tau, right? And I can, if like we said, I mean, we are limiting ourselves to functions that have u of t in them. They are something multiplied by u of t. Since we are limiting ourselves to those kind of functions will always be 0 somewhere, right? So it's going to be 0 somewhere, and then we will have the function continue. That's because this function, we are always going to assume that it's going to be something times u of t. U of t is always going to be a zero below certain value of t. Below 0, of course. I could have u of t minus 5, for example, which is still allowed, or plus 5. Okay. The idea is that there is a portion towards minus infinity where the function will be 0. So a really could be anything. I can make a very small. I can choose a to be where the function is 0, and I can make it anything. So this is equivalent, using this argument, this is equivalent to making a minus infinity. Nothing will change if all our functions have this property. Right, so this is equivalent to integral from minus infinity to t f tau d tau. Now the question is, what is the Laplace transform of this with respect to the Laplace transform of f? So if we know the Laplace transform of f is f of s, what is the Laplace transform of the integral? Right. So there is one way to visualize this and try to figure this out. What is integration? Integration is really summation. So we're summing all the values of f at a certain point. Right? We're summing all the values of f and we're multiplying by so if we take a general function, let's say, we sum all the values of the function. That's what integration is, finding the area. And then we to find the area, we multiply by h, by the distance between those sample points, and then we take h to 0. That's what integration is. So, but the first act of integration, before we multiply by h, is we sum the signal at different points. So if I'm finding the integral at a certain point, what is this equivalent to is I'm taking my function, I'm shifting it by a certain amount to the right and to the left. So I'm shifting it. This is, let's say, ft minus h, and this is ft plus h, right? But I'm shifting it by any amount. I'm shifting it by ft minus 1h, ft minus 2h, right? So I'm shifting the function by different integer values of h, and then I'm summing everything to get the integral. That's one way of looking at the integral. So I could rewrite integral from minus infinity to t of f tau d tau as being a sum over k of ft, a sum of the shifted versions of f, right? Times h, and this is limit as h approaches 0. This is just the Riemann sum. This is a restatement of the Riemann sum definition of the integral. Think about it. I mean, we're just summing all the values of the function. And how are we reaching all the values of the function? By shifting the function by different amounts, multiplying it by h to get the area, the small areas, and summing up all the small areas to get the integral. Right? Now we can apply the Laplace transform to this term, because this is simply a shift, right? This is simply a translation. So we know that this is equal to limit as h goes to 0, sum over k of e minus k, lambda in this case is minus k, sorry, lambda is minus kh, right? So e minus kh s f of s times s. Now we want to evaluate what this would be. Notice that e minus, sorry, fs and h is not a function of k, so this equals limit h goes to 0, fs h, sum over k of e minus hsk. I can take the k out like this, right? Notice that this is a geometric series. Oh, this is something you learned in calculus. You know the series k to the x to the k over over k, right? And we know how to sum this. This is 1 over 1 minus x. Of course, this is true if x is less than 1, right? So this is a result from calculus. The idea here is because h is small, very small, approaching 0, this term is going to be less than 1. So we can sum up this geometric series. So we end up with integral from a to t of f tau d tau. The Laplace transform of this is going to be f of s h of h, right? And this is a geometric series I'm going to write the sum of. The sum is going to be 1 over 1 minus e minus hs. This is limit as h approaches 0. Okay, we can do further. We can approximate this E by truncating it, taking the Taylor series expansion and truncating the higher order terms. We can do that. So this is equivalent to f of s, because h is small, h 1 over 1 minus 1 minus hs, so it's become 1 minus 1 plus hs. This cancels with this, h cancels with h, and we end up with the integral of a function being transformed as the same f of s of f divided by s. So this is the mirror result for integration. For differentiation, we found that the differentiation is simply, in the s domain, is simply multiplying by s. Integration in the s domain is just dividing by s. Notice we turned like something that's really complicated in the time domain. Finding integrals in the time domain is not a trivial thing, but we turn that into a very simple division by s in the s domain. This is a major simplification to differentiation and integration that is achieved by just moving, reparameterizing the function, moving from the t domain to the s domain. It turns out that the Laplace transform has a property that can be derived from the basic definition, and I'm going to state it here. Laplace transform is skew symmetric. What do I mean by skew symmetric? And this is a property, by the way, that you could derive from the basic definition. Right? But I want to state what it means. What is skew symmetric? Skew symmetric means that if there is something you can do, if the Laplace transform has a certain property, when you transform from t domain to the s domain, you can utilize that property to go to the opposite way from the s domain to the t domain, but then instead of s, you need to substitute minus t. I mean, this is clearest by example. What I want to show you what it means by example. Otherwise, it's hard to understand. So we established that if I have df of t by dt, we established that can be transformed to sfs. Okay, so we established this property. But because the Laplace transform is skew symmetric, we can also find the differentiation of f of s, right? I could find what dfs over ds is. How does this transform into the t domain, right? Using the inverse Laplace transform, right? Due to the skew symmetry of the Laplace transform, I can find this from this, right? It's going to be the same thing. It should be symmetric, but it's going to be skew, meaning instead of s, I'm going to put minus t, right? So here, dft by dt goes to sfs. Using skew symmetry, that means dfs by ds should go to t ft. So s goes to t. Because it's skew symmetric, instead of t, I'm going to put minus t. Right? And you could rederive this from the defining property. We can take the differentiation definition of dfs by ds and start from there to get this result. We will get the same result. But we also got it from just applying skew symmetry. So the Laplace transform is skew symmetric. That's example 1. Example 2, well, I mean, the defining property 3 is clearly skew symmetric. It's baked in, right? even the defining property itself is skew-symmetric, right? Because, you know, if we have ft plus lambda, that goes to f lambda s fs. Well, what happens if I have f s plus lambda, right? So that goes, I mean, skew symmetry applies, so it should be the same. Going from s to t should be the same as going from t to s. So this should be e lambda t. Now we're going to the t domain instead of the s domain, ft. But remember, instead of t, we want to put minus t. So this is going to be e minus lambda t. Right? So clearly the defining property itself is skew symmetric. Example 3 of skew symmetry. When we say it, integral of f tau d tau from a to tau to t is just simply fs over s. Well, then what is the integral from a to s of s, I don't know, u du? Right? So this is a function of s. Again, skew symmetry applies. Whatever happens from here to here should also happen in reverse if the s function has the same form, right? So this should be just f of t over t, but instead of t, because it's skew symmetric, we need to put minus t. So this is going to be minus ft over t. Okay? So this is also a result that follows from skew symmetry. This might be harder to find from basic principles, but if we know that skew symmetry always applies, this is easy result to get using skew symmetry. Be careful here for this integral to converge. If s must approach 0 as s approaches infinity. Okay. So yeah, so we have everything we need at this point to start. I mean, we've defined the Laplace transform. That's it. There's nothing more to it. Now the question is, how can we get the Laplace transform for different functions? Up to this point, we only know how to get the Laplace transform for delta t. Right? So delta t goes to 1. That's it. We don't know how to get the Laplace transform for any other function. But we have enough tools at our disposal right now. We have the basic defining property, the 4 defining properties: invertibility, uniqueness, and linearity, and then the time shift and frequency shift property, as t shift and s shift property, or t translation and s translation property, and then finally the delta function transform. That's enough. I'm claiming that that's enough to find the Laplace transform for any elementary functions. Oh, and by the way, we use those properties to find out how differentiation and integration affects the Laplace transform. Okay. So we already know how to handle u of t, right? We want to find the Laplace transform of u of t. We know that u prime of t equals delta t. We've established that last lecture, right? So we know that the Laplace transform of delta t, which is u prime of t, equals 1. We know we established the basic result that the Laplace transform of differentiation of a function is just s times the Laplace transform of that function equals 1. So that tells me that the Laplace transform of u of t equals 1 over s. So, okay, we inched forward a little bit. We expanded our table. Initially, we only knew delta t. Now we know how to transform delta t and u of t. So we're inched forward. We added an element to our table. So we started with delta t, which transforms to 1. Then we went to u of t, which transforms to 1 over s. Right? And then we can expand this table further. It's not that hard, and I'll show you how to do that. We can expand this table to all elementary functions without even doing integration, using the integral definition, which I will get to too. Starting from what I'm trying to say is moving forward now, we want to build up this table, but we want to now change the notation a little bit. We said we wanted to only consider functions that have u of t in them, right? Why? Because those functions make differentiation unique, right? They make it an invertible operation, and they're essential for the Laplace transform. It's always essential to have u of t for functions, or delta of t for functions where we want to do the Laplace transform. So moving forward, I won't just write f of t, I would write f of t, u of t. All our functions will be of this form. There will be some continuous thing, but function multiplied by u of t. Even if sometimes I forget to write u of t, when we're dealing with the Laplace transform, you should implicitly assume that there's a u of t there. Right? So this is the notation that we will do. So I would write something like this. So f of t will always have u of t tagged to it, and the Laplace transform of this is going to be f of s. So this is a pair that you will see always, something like that. You will see some function of t where it's decomposed into the actual function times u of t, and then it goes into f of s. All right. Let's see. So we want to start populating the table and the table of functions. Let's do that next time. All right. Thank you, guys.